As he said, my name is Ben Darnell. I'm the co-founder and CTO of Cockroach Labs. And I'm here today to talk to you about how and why you should run your database like a CDN to optimize your application's performance for a global audience. So to give you a preview of the rest of the talk, I'm going to first explain what it is exactly I'm talking about when I say run your database like a CDN. And then I'll walk through an example using a fictional startup called Mover, and then explain some of the different replication strategies that you may want to use to keep your data distributed across the globe. And then I'll wrap everything up. So for those of you that haven't heard of CockroachDB, it's a distributed, consistent SQL transactional database. So for OLTP workloads, open source with an enterprise edition available. This is not strictly a talk about CockroachDB. It's more about general principles that you can apply to any database, of course, including Cockroach. So first of all, just to get everyone on the same page, what is a CDN? So a CDN, or a content delivery network, is a global network of servers and caches. These are commonly used for static content. You're probably familiar with them. They're available from many commercial providers, including Cloudflare, Fastly, Akamai, Amazon, and other cloud providers. And so the goal with the CDN is to get your data distributed around the world so that the data can come from a server that's closest to the user. Now, why is this important? Well, if we consider the alternative, if you didn't have a CDN, if you just had a single web server somewhere in the world, then all the traffic from all of your users has to come to that one place. And the problem with this is the speed of light. It takes a significant amount of time for data to travel around the globe. So from Amsterdam to New York, it takes about 80 milliseconds. 170 milliseconds to South Africa, over a quarter of a second to parts of Asia or the southern hemisphere. And so this is really noticeable. Amazon and Google have done a lot of studies to show that a quarter of a second delay in serving requests actually meaningfully changes your application's conversion rate, and this can cost you sales and business. And in a database, this can be compounded by the fact that many applications have to make multiple round trips to their database while servicing a single request, and this can cause these delays to be multiplied. So for static content, the usual solution for this is a CDN. This gives you a network of servers distributed around the world so that users always have a nearby host to talk to. And this is all. This has become a lot easier than it used to be with the rise of cloud providers, because it's very easy now to get machines set up in many different locations around the world. So CDNs are a nice solution to this problem for static content. Now, why are databases different? Why do we still have this problem for databases? Well, the first reason is that it comes down to how this data gets updated. With a content delivery network, it's used for mostly static content. It can be updated, frequently, many times a day potentially, but that's still not very common in the grand scheme of computer speeds. And it's also a mostly centralized process. You have a content management system running somewhere, which is responsible for feeding your updated content into the CDN. And this is a relatively centralized process. The details can vary depending on how you work, but it's mostly controlled from within your organization. Finally, CDNs can generally get by with a fairly relaxed consistency model. They sometimes need to do atomic swaps of multiple units, but for the most part, you're okay with asynchronous replication and the fact that it may take a fraction of a second or many seconds potentially for your data to make it around the globe. In a transactional database, on the other hand, your updates are very frequent, often in the thousands per second. They're typically consumer initiated. So this would be whenever a user adds something to their shopping cart, for example. This this is a typical transaction that needs to be very fast. And it's used in very complex ways by your application, which is easiest to build if you can rely on consistency from the database. If you don't have consistency, if you're working in an eventually consistent model, then it becomes a lot harder to develop your application because you can never be sure whether what you're seeing is the latest data. And the second reason why CDNs are not applicable to, or we can't just directly take the lessons of CDNs and apply it to databases, is that for a long time databases just weren't cut out for this kind of task. In the 90s, you might replicate your data for fault tolerance, and that would be it. That you'd have two servers right next to each other, or maybe in two different data centers, but you weren't really thinking about getting your data distributed for performance reasons. The same thing in the 2000s with the rise of the NoSQL movement. You would shard your data for scalability, and NoSQL in fact made significant sacrifices in data model and flexibility in order to make that sharding easy to do. But again, it was performance was a secondary concern, and in both of these scenarios, you would think about distributing your database as a price to be paid in terms of performance. It wasn't necessarily giving you better performance on your user-facing queries. But now in 2018, we think it's time to distribute your data around the world explicitly for performance and improving latency for your users. And the capabilities, both in terms of cloud infrastructure and specific database technologies, have gotten to the point where this is a good idea. And so now, with a distributed database, you can achieve better latency for your users than is possible with a more centralized solution. So the big lesson that I want to impart in this talk is that a database is not just a place to store your data, it's a tool to get that data where it's going to be needed. So now I'm going to walk you through the story of Mover, which is a fictional vehicle sharing startup. This is that they do vehicle sharing, cars, bikes, scooters, skis, ice skates, boats, basically any kind of vehicle that the Unicode Consortium has decided to make into an emoji. And they launched in Amsterdam last year and are looking at expanding globally. So the reason that we chose a vehicle sharing application as an example here is because it's a good illustration of a couple of different types of data that we can explore in some detail here. So the two main categories of data are exemplified by the vehicle data, which is tied to a particular city. It's updated very frequently. And this is really the most important data that Mover has in terms of the user perceived performance of the app. Because every time you start up the app, it's got to load up a list of the available vehicles and show you where they are. The second category of user data data is user data. Users are also associated with a home city, but they can move around. When you're on holiday in another country, you want to be able to use your same Mover account to get a bike, even when you're far away from home. This data is also updated generally less frequently than the vehicle data, and it can be cached pretty aggressively in the app because the user is only modifying their own data. There's not as many updates that cross from one user to another. So we'll be talking about different replication strategies for these two types of data as we walk through this example. So phase one of Mover's launch, they were in a single city. So Mover launched in Amsterdam with one data center. Just because you're using a distributed database doesn't mean you have to distribute everything from day one. It can be a lot simpler to start out with a single location and scale up from there as you need it. The first reason that Mover decided to scale out and replicate their data was actually for fault tolerance, because their operations people were getting paged in the middle of the night, and that was no good. So you want to make sure that the application is always available, and so you can replicate across multiple data centers in a single region. And so here, when you have Amsterdam, Berlin, and Paris, it's all pretty close together in terms of as far as the speed of light goes. It's only a few milliseconds or tens of milliseconds between these locations, and so that is not going to be much of a performance problem for your users. In the next phase, Mover expanded into more cities. So starting out elsewhere in Europe. And the latency is pretty good from Stockholm, Rome, Madrid, anywhere else in Europe. It's pretty good latency just within the region. But when you expand further out to the rest of the world, then things start to get more complicated, because now you have the speed of light coming back into the equation. If you just keep your setup with a few servers in Europe, then you're back to having 200 millisecond plus latencies for your users on the other side of the world. And if you just take your three data centers out of Europe and spread them around, put one in New York, one in Tokyo, and leave one in Europe, then that addresses part of the problem. It lets you read your data from all of these different locations much more quickly. But if you're writing the data, then that data still has to be replicated across long distances, and that is expensive. And so the solution for that, what I think is the best solution for that preserves both read and write performance, is to subdivide your system into multiple subclusters that can be within a region, and put your localized data there. So now I'm going to go into some more detail about how exactly you can achieve this by replicating your data both within and across regions as appropriate. One way you could do this is just by using completely separate databases. You could have a Mover Europe database, a Mover Asia database, and a Mover America database, which would serve the different regions. But this is a very cumbersome solution, because it's operationally complicated to manage the three separate clusters, and you can't do transactions across your different databases, which can be a problem when you're dealing with users that can move around and want to be able to use the service when they're traveling internationally. So in CockroachDB, we have the solution that you can have everything replicated in both ways. You can have one giant cluster that spans the globe, and you can also subdivide specific tables and locate data in different regions. And so this gives you the flexibility to choose the right replication model for particular types of data in your application. So to explain in more detail how exactly replication works in CockroachDB, first of all, from the application's perspective, it looks just like one big database. There's no user-visible distinction that you're having to cross these regions or other boundaries. There's no restrictions on what you can do in transactions. Your tables can scale up and down as much as you need, and you can do transactions that span the entire globe if you need to. But we also give you fine-grained control over where exactly your data lives. We have this both at the table level and at the row level. And as I said, transactions can include data even when it spans different regions. CockroachDB's replication is based on quorum or consensus model. This means that each record has 3 or more replicas. One of these is the leader at any time. You would typically have odd numbers of replicas, because that gives you a way to break ties. So typically you'd use 3 or 5 or maybe 7 replicas, depending on your application's needs. And whenever you want to write to the data, that write has to go to a majority of the replicas. We replicate data synchronously as part of our guarantee of fault tolerance and consistency. This means that by the time your commit statement has returned to the application, your data is persisted on multiple data centers, and so you can be sure that it will be available even in the event of machine or data center failure. So writes talk to a majority of nodes. Reads go to the leader because the leader is guaranteed to be up to date. But it may not necessarily be the nearest replica in the replica set. So to go through a specific example of this using data from Mover, we're going to look at the vehicle data first. This is the data that is most strongly localized in the system. It's the vehicles are tied to a city. For the purposes of our data model, they never move from one city to another. And so here it's really important that the reads and writes are both fast from within the region. And so you don't want to just replicate the data globally, because then you may have to talk remotely to get your 2 out of 3 or 3 out of 5 majority in order to commit the write. And so in a simple global replication setup, your reads can still be good, because if you're reading from Vancouver, for example, then that read can be served from New York. You're still not crossing an ocean, and so that can be done within about 70 milliseconds. But when you want to write, this is more complicated. It's because the writes have to go to a majority, and so your write is going to go first to New York to get into the system, and then to Amsterdam, or whatever your next closest replica is. And so then you have to add this up, and so writing to a globally replicated table is going to take, in this case, 150 milliseconds. And so that's not ideal. So we want to get that down get that down to something that can be done within the North American region. So the way we set this up is a 3-step process. First, you configure the servers. This is an abbreviated look at what it takes to start up a CockroachDB cluster. You can give each server a locality parameter, which tells the server where it fits in your data arrangement. And this gives you a customizable hierarchy to distribute your data across different data centers and different regions and availability zones. And whenever you start up a Cockroach cluster, it's very simple. You just it's a single process that you run, and you give each node a join parameter that tells it where it can find the other members of the cluster. Step 2 is to partition the data. So we have some SQL extensions that we use to change the table for a partitioned use case. The first thing to note about this create table statement is that we have a composite primary key that includes both the country code and the UUID for the vehicle. This is important because we see the partitioning and the location information as the first part of the primary key. Primary key, or in some databases it's called a cluster key, is used to determine where a record lives on disk in a non-distributed database, and so we've extended that concept to control where the data lives in our distributed database. So first of all, in order to partition a table, you need to give it a primary key such that the first part of the key gives you the location. And then you tell the server a little bit more about how exactly you want to partition it. In this case, we want to map our country codes into a couple of zone names, and this is a convenient convenience that you can use so that you don't have to refer to dozens of different configurations per country. You can do this just based on the number of regions that you have. And then you have the flexibility to change that mapping so that as you add new regions, you can change this later. Finally, you configure the replication itself, and so this is a simple, well, relatively simple. It's a little ugly. We're working on better syntax for this, but it's a single invocation to set the configuration for the Europe partition of the mover.vehicles table. To give it a constraint that it needs 3 replicas with region equals EU. And so this is what ties the locality flags from the server configurations together with the partition names in the table definition. So with this configuration, what does our replication time look like now? So now we have 3 servers in the US, in New York, Denver, and Miami. And so when you now try to write from Vancouver, that write goes to Denver and New York instead of New York and Amsterdam. And so this takes about 85 milliseconds instead of the 150 milliseconds that we saw previously. So we've almost cut the latency in half. And this, by the way, is kind of an artificial example. I chose these cities to give you a nice big triangle on the map that's easily visible. But in practice, you could move these data centers closer together and typically get even better performance. So the second type of data that we look at is the user data. So the user data, as I said, the users are associated with a home city generally. So you could replicate it the same way, give them a city or country code in their primary key and store the data tied to a particular region. And that's going to be the best thing for write performance. And so if you're writing to this user data a lot, that may be the way you want to go. But I think that the interesting case here is that if you care more about read performance than write performance, and your users are mobile and may travel around the world a lot, then you can actually get better read performance by replicating them globally. And one of the things that empowers this, the reason that this is important is because the read performance depends on where the leader is. Reads go to a single node. And this node is going to vary on a range by range or record by record basis. And so the really powerful thing that makes it possible to use this as a strategy for your user data is a trick that CockroachDB supports called follow the sun. And so this is based on the observation that any sort of application is going to have daily patterns in its usage. It's going to be tied to time zones and daytime around the world. Depending on your application, that peak may not always be the same. Some applications have a peak during the workday. Some applications like Netflix have their peak in the evenings. But it's still going to follow a global daily cycle in which you see the traffic kind of moving in a wave around the globe. And so in CockroachDB, we recognize this, and for your data that is replicated globally, we can move the leadership from one region to another. And so that as the sun moves around the world, the load can move with it. And so when most of your traffic is coming from Europe and Africa, then the leadership is going to be placed in Europe. When it's coming from the Americas, then the leadership will be in that region, and so on when it comes back around to Asia. And so this is a very powerful technique that's very straightforward to use. In fact, you don't really have to do anything. It happens automatically in CockroachDB as long as your data is your access patterns follow this sort of distribution. So, in conclusion, your users are global, so your data should be too. You should think of geographic replication of your database as a tool to improve your performance, and not just a way to get fault tolerance and scalability. And also to think about the fact that different tables may need different replication strategies. So it's important to understand your application's requirements and access patterns in order to get the best performance. So we've looked at 3 different replication patterns in this talk. So to recap, if you're mainly concerned about high availability, then you actually don't want to bother with global geographic distribution. You want to just keep your servers close together in a single region. This is going to give you the best write performance, and as long as your data or your users are mostly coming from a particular region, then that's all you need. For data that can take advantage of the follow the sun workload pattern, then you want to replicate that globally across regions to give the rebalancing process enough tools to find the the right place to put the data and its leader. And finally, if your data is very strongly associated with a particular location and you want to optimize for write performance, then you can replicate within separate regional groups to keep that data in place. So, finally, CockroachDB is a great database to use if you're looking to explore this strategy. It was designed for global replication from the ground up, and it gives you this kind of control over where the data is placed to let you bring the data to the user. And now I know I'm the last thing standing between you and lunch, so I'll wrap this up and be happy to take some questions. Also, these are our websites. We have our main website is cockroachlabs.com, and we have a blog post at cockro.ch/CDN lessons which talks more about this particular topic. So, thank you very much.
Thank you, Ben. I have a few questions. If anyone wants to ask, please approach the mic. How do you deal with multi-tenancy? Are there out-of-the-box features?
How do I deal with multi-tenancy in CockroachDB? Well, currently, we have the standard sorts of SQL permission systems, so you can create databases and tables and users and grant permissions on them. We don't yet have good enforcement of quotas and things like that, so it's not yet ideal for significant multi-tenant usage, but that's on the roadmap for future development.
Hi. I want to ask what replication strategies do you support for replication in globally? Like, is it asynchronous replication, asynchronous replication? How many replicas do you need to receive data for consensus? Can you elaborate on that, please?
Right. So in terms of replication strategies for global usage, all of our replication is synchronous. So by the time your transaction commit returns, the data will be fully replicated to a majority of nodes, so that it'll be durable and persisted. And we require an odd number of nodes just for tie-breaking purposes. So the minimum number of replicas. Well, you can run in a single node, but as soon as you have more than one node, then the minimum is 3 in order to make sure that you can have a tie-breaking vote in the leadership elections. And then, so from there, it's every write goes to 2 out of 3 or 3 out of 5 or so on replicas. Does that answer the question?
Yeah. So it's the only strategy.
Yeah, this is the only option. You can choose you can choose how many replicas you want and where those replicas live. But we don't offer eventual consistency or asynchronous replication as options.
I see. Yeah. Thank you.
If you want that model, then you can just perform your commit in like a background thread and just return to the user before it's done, and that's basically the same thing.
Okay, I have also a question for you for my own interest. Are you aware of Datomic database? And if so, can you highlight some of the differences?
Yeah, so I'm aware of Datomic. I'm not. It's been a while since I've looked at it in enough detail to be able to say much about it. I think the biggest and most obvious difference is just that CockroachDB is a SQL database, and so that is our application interface, and so that gives you something that's much more compatible with a lot of existing applications and frameworks. I know that Datomic is built on immutability and sort of the functional programming style of immutable objects, and we don't have that. We're more in the SQL model where rows and tuples can be updated. So those are the things that the differences that I'm aware of off the top of my head.
What about optimistic locking to reduce latency? Could a devices from Quorum decide on transaction consistency?
Yeah, so cockroaches, so optimistic locking is a surprisingly deep and complex subject here in CockroachDB. Our transaction model has always used a combination of optimistic and pessimistic locks. Over time, we initially described our transaction model as mostly based on optimistic concurrency control. Over time, we've shifted more in the direction of pessimism and locking, and that has caught a few people by surprise. But all of this, there's no potential for inconsistency here. In the sense that the transaction model, because everything goes to a majority, or because all writes go to a majority and all reads go to the leader, there are always guarantees that no data will be lost or and no transaction will be allowed to commit if it's inconsistent with another transaction that's already committed. The one case where our use of optimistic concurrency can be an issue is that this is why we're currently unable to offer the SQL select for update statement in a way that a lot of people like to use as an advisory lock. That's just not compatible with the amount of optimism in our transaction model, because your transaction can be aborted out from under you by a conflicting transaction and have to be aborted and retried.
For a single region and no need for application within the region, is CockroachDB more suitable than Postgres or MySQL?
So is CockroachDB more suitable than Postgres or MySQL for within region use? I think that's going to be up to your application, but I think it certainly can be a good solution even when you're just replicating locally. We've put a lot of work into making it much easier to set up replication in CockroachDB than in either MySQL or Postgres, and then it scales horizontally, transparently. You can just add more nodes, and it scales both up and down. You can run an instance of CockroachDB on your laptop, which is a nice point of comparison against something like Dynamo or Cosmos DB. We don't have, of course, that's not an advantage in comparison to MySQL or Postgres. But yeah, I think we've tried to make the database scale both up and down so that it's a viable solution at every level.
What do you use to maintain quorum state? A console, Zookeeper, console?
Right. So the quorum state is used with a Raft library that is embedded in the application. So Raft is a consensus algorithm. It's an alternative to Paxos, and so that's what we use. We actually share the implementation of Raft with CoreOS's etcd. But we don't use an external service like Zookeeper or Console or etcd for anything. Everything is managed internally to Cockroach. It's just a single process that does everything.
How does CockroachDB compare to DynamoDB, global tables?
Right. So DynamoDB is a non-SQL database. So again, it's got a very different programming model. So I used DynamoDB on my previous project, but that's been 4 years ago now. So my information here may be a little out of date. I know that 4 years ago it didn't have good support for transactions, and we ended up having to work around that a lot in our application. I believe it does have transactions now, and so it's become a lot closer, but it still doesn't have these sorts of global replication that you can do with CockroachDB, as far as I know.
How does CockroachDB find out about follow the sun? Do you configure GPS coordinates or?
No, so the follow the sun is not based on GPS coordinates. Cockroach doesn't know anything about where the sun is. It just knows where the traffic is coming from. And so if a node, the nodes are in constant communication and exchanging metrics. And so if a node discovers that it's getting, that a lot of queries for a particular piece of data are being routed through a particular region, then it will detect this and move the leadership from one place to another. The only reason Cockroach needs to know about latitude and longitude coordinates is if you want to have things displayed nicely on a map in our admin web UI.
Any other questions? And the last one is, what other dynamic leader selection method next to follow the sun do you expect to have in the future?
So after follow the sun, I think the general so I mean it's not just follow the sun, it's follow the traffic or follow the workload. So it does work, you know, whether your traffic patterns shift for you know, reasons of daytime or something else. So it is a little more general than that. But other than that, I think we have the next thing on the list is that right now follow the sun works for changing for moving the leader of a range, but it can only choose a leader from among the replicas from the nodes that happen to have a replica of the range. And so, sort of our next generation dynamic balancing system will be able to move the data itself to a more suitable location based on where the traffic is coming from.
Yeah. So you mentioned before that you that CockroachDB is also viable as a normal database. That is not necessarily around the whole world. Mm-hmm. But did you make any design or architecture trade-offs that towards a fully distributed system where you suffer penalties on the local setups?
Yeah, I think there are some things where we may not be. We're not optimal at smaller scales because of some of the decisions that we've made to support distributed execution. So yeah, like you can if you run CockroachDB as a single node instance, it's not going to be able to match the performance of a single node of MySQL or Postgres, and that's just because there's a lot more internal overhead because everything is designed to be able to work over the network. So yeah, you do pay a bit of a performance price at the smaller scales, but in return you get the ability to scale up very easily and relatively cheaply as you need more performance.
Thank you, Ben.